Hi, Christian. Hi, Rolf. Are you guys already in chat? That's awesome. Thank you very much for joining the stream. We'll start in a few minutes. Oh, hi, Vernon. Thank you very much for joining the stream. How's everyone doing? Okay. By the way, this is the so-called Holder's inequality. Even though I think somebody before Holder invented it, I mean discovered it. Um, so we'll get to this inequality when we introduce integration. This is quite important in probability and PDEs, for example. This is a generalization of the Cauchy-Schwarz inequality. Not in L2, not necessarily in L2, but for LP spaces. It's pretty cool stuff. Okay, so here we would probably continue. We'll definitely continue sigma algebra today, and let's see how far we can go. Poke ball. Okay. Anyway, so why don't we just get started? Huh? So let's see the notion of sigma algebra. Let's just do a brief recap of why do we need sigma algebras and what is a sigma algebra, because we introduced the notion of sigma algebra last time. So first of all, sigma algebra is a collection of subsets. Okay, it's a collection of subsets. Given a universal set, the biggest collection of subsets is, of course, the power set. Sigma algebra is a smaller class. Is a smaller class of subsets. Okay, it is particularly important in measure theory because of a disappointing result. And here's that disappointing result. Okay, we were talking about outer measure. We've been talking about outer measure in our previous stream, and outer measures has some good properties and some not so great properties. And in particular, one annoying feature of the outer measure is that it is not additive. Basically, there exist disjoint sets A and B such that the outer measure of A union B is not the sum of the outer measures of each set. Okay, that's an annoying feature. And it turns out that this isn't just a feature that is special to outer measure. Okay, in a sense, the ideal notion of size simply does not exist. And here's that result: the non-existence of extension of length to all subsets of real. So let's look at these desirable properties. We want, ideally, a function mu, which is the extension of length to all subsets of real. So how should mu behave? Well, mu takes an arbitrary subset of real to 0 to infinity. Next, it needs to agree with the usual notion of length for intervals, for open intervals. Okay, outer measure satisfies this result. C, that's the additivity, in particular countable additivity. Countable additivity, it says if you have a disjoint, this is important, a disjoint sequence, A1, A2, and so on, not the outer measure, but the mu value. Okay, this is an abstract function. We don't even know what that is, but we want it to satisfy this property. Mu of the union of all the AKs is the series or the sum of the mu of AK. So C. Now C is the countable additivity. This is extremely important because later on we will see in the Lebesgue theory of integration, this is where a lot of the nice things happen. Now, this is the reason a lot of the nice things happen, when you can interchange the limits and integrals. So C is absolutely crucial. We want C to hold. And D is the behavior of mu under rigid motion. Okay, so if we translate a set A, mu should not change. These are all very natural properties. Unfortunately, it does not exist. Such mu does not exist. That is to say, A, B, C, D are mutually contradictory. Okay, so this put us in a bit of a dilemma. We want all of them to hold, but logic does not allow that. So what we decide to do is we keep B, C, D. We keep B, C, D, and instead we give up A. Or actually we take a reconversion of A. So because of the existence of so-called non-measurable sets, the construction requires the axiom of choice. This is shown in the proof for the non-additivity of outer measure. There are weird sets in R basically, and we don't want to deal with them. Okay, so we simply restrict this the domain of mu basically, and that domain of mu is the sigma algebra. Okay, so that's the technical reason why we need sigma algebra. It is highly non-trivial. Okay, so the definition of sigma algebra is quite intuitive, and in fact this is usually the starting point of measure theoretic probability. If you take a measure theoretic probability class, without assuming measure theory, this is where you start from, sigma algebra. So the definition of sigma algebra, let's go over that again, because pretty much the whole stream will be using this throughout. Okay. Definition, sigma algebra. Suppose X is a set, and scripted S is a set of subsets of X. Then the scripted S is called a sigma algebra on X if the following three conditions are satisfied. Okay. One, the empty set must be in scripted S. So scripted S is a non-empty collection. Okay. So we usually avoid the phrase the set of subsets. Okay, for no mathematical reason other than just linguistic reason. Okay, set of subsets sounds a little bit redundant. High ND. We usually say family of subsets or collection of subsets, that sort of thing. Okay. So basically, this is a non-empty collection. The first bullet point tells us it's a non-empty collection. The second bullet point says if E is in S, then X minus E is in S. So that's complement. X minus E, the set difference, is complement. So second bullet point says a sigma algebra is closed under complement, complementation. Okay, so immediately from the first two bullet points, we see that X itself is also in S. Right? Because from 1, we know the empty set is in S, and X minus the empty set, of course, is X itself. So this tells us that any sigma algebra must at least have two elements: the universal set and the empty set. And in fact, this is called the smallest sigma algebra. Smaller sigma algebra. If we recall, in linear algebra, the smallest vector space is just a vector space with zero vector. A vector space can never be empty. It must contain at least. Does that imply independence? No, this has nothing to do with independence. Okay, and this has nothing to do with independence. Okay. Okay, interesting. Apparently in Danish they call it paving. or a collection or subset? I have no idea. It's very interesting. Unable to follow the stream at my time zone, was gladly waiting for this video. Okay, sorry about that. So this is because my biggest audience is in North America, and this is North American time, and it's also convenient for me. Yeah, if you're unable to join, that's okay. That's totally okay. I'm just glad you're interested in the content. Thank you very much for your support. So ND, this has nothing to do with independence. Independence is a very much a notion that is unique to probability theory. This has nothing to do with independence whatsoever. So if we recall basic probability theory, if you have two events, they're called independent if their intersection has a probability equals to the product of PA times PB. That's independent. So you see, we don't even have a notion of P yet. Right? P is a notion of a measure. We don't even have a notion of measure yet. Okay, so this is an extremely primitive notion, sigma algebra. So back to the last bullet point. If E1 all the way is a sequence of elements in S, then their union, the union of all the EKs is also in S. You guys are 1 p.m. or 1 a.m. Roth. You guys are in. Okay. I see. I might need to do a little bit of a poll, or just to say, because I do want more people to join the live stream. I mean, I just made an assumption that most of, I mean, it's not an assumption, but according to my YouTube analytics, most of my viewers are in North America, but for measure theory in particular, I don't know what's the dominant time zone. If you guys can type in chat, that would be great. So that's the definition of sigma algebra. Coming from applied science, I'm still learning. That's great. Awesome. Yeah, so sigma algebra in probabilistic language, is described as follows. 6 p.m. here. That's great. So it's an hour. It's 7 p.m. here. I'm on my end. So basically, sigma algebra in probability theory is said to consist of events. In probability theory, we write this. So in probability theory, we have something called a probability space. A probability space, hi Shan, thank you very much. So a probability space is a triple. Usually write it as omega fp. It's really written as omega fp. So here, omega is the set of outcomes called the sample space. Okay, and F, scripted F, is the sigma algebra. Is a sigma algebra on big omega. And P is the probability measure, which we will define it later. Okay, so that's a triple called probability space, omega Fp. So everything in the sigma algebra are called events. Right? Every set in sigma algebra is called an event. In elementary probability theory, we usually just call an event a subset of the sample space, a subset of omega. For elementary probability theory, that's usually enough because you deal with measurable sets anyway. Right? And at that level, introducing the notion of measurability is more likely to cause confusion for beginners rather than helping them. So that's a technicality that elementary probability theory, introduction to elementary probability theory, omit entirely for a very good reason and a totally valid reason. So here, because now we're dealing with rigorous measure theory, we have this notion of sigma algebra. So sigma algebra in probability theory are called collection of events. Every set in F is called an event. Set of events, all the events that we consider. Hi, Mala. So in probabilistic language, we say the impossible event is an event. Okay, the empty set stands for event that is impossible. That's the interpretation of the empty set, because it contains no outcome. Right? Remember, omega is the sample space, and the elements in omega are called outcomes. Omega consists of all outcomes. Okay, in probability theory, we say the event that consists of no outcome, basically impossibility, is an event. Okay, and second bullet point says, if E is an event, then not E is also an event. So there's that, kind of intuitive, right? And the last one says, if you have a countable collection of events, then their union is also an event. So that's basically what sigma algebra is about. Sigma algebra is all about the domain of measure. Remember, here our original aspiration is to assign a notion of size to all subsets of real. But that's just too ambitious. Okay, it causes logical difficulties. So that's why we step back from A and instead just talk about the function that maps from the sigma algebra to 0 to infinity. So this notion of sigma algebra is all about the domain of measure. Domain as a domain in the notion of functions domain. Okay, because measure is a function. It takes a set as an input and it returns an extended positive real, extended non-negative real as an output. Okay, and in the last stream, at the very end of it, we did these verifications, examples of sigma algebra. Let's just briefly go over them. Well, you can check the last stream's recording to see the details. As we mentioned, the smallest sigma algebra, right, is this one, is the empty set in X. Next, the largest sigma algebra, the collection of all subsets, the power set, usually denoted as scripted P of X. So that's the power set. The power set is obviously another sigma algebra. And the last one is a little bit more interesting, because typically the interesting sigma algebras are between the smallest and the largest. Okay, typically speaking, we want to study sigma algebras that are somewhere in the middle. We don't want all the subsets, and we don't want just two. Usually interesting stuff happens in the middle. Okay, so the third one is one that is in the middle. Okay, let X be a set. The set of all subsets of subset E of X such that E is countable, or the complement of E is countable, is a sigma algebra on X. So let's write that. This is S. S in the third bullet point is defined as E subset of X such that E countable or X minus E countable. Okay, so that's the third one. Proving this is a little bit less trivial. It's not that difficult. It's proving this a little bit less trivial than the first two. So this is the examples of sigma algebra. Right, let's continue. Actually, I just wanted to mention. Okay, I got some feedback from viewers that the first two streams were a little bit heavy. Okay, in terms of the content, it's a little bit dense, which is totally understandable. Okay, the first two streams, when we discuss outer measure, is a little bit dense. Okay, first of all, it assumes the basics of elementary analysis, things like soup and inf. Okay, even though it's not a terribly involved concept, but typically speaking, if you're new to analysis, you still need some time to get a hang of it, right? And then we did two difficult proofs, in my opinion, two difficult proofs. So one is the union, sorry, not the union, but one is the outer measure of the closed interval. Right? It looks rather innocent, but it's not easy to prove. So this is the one we did last time. The outer measure of a closed interval a to b is b minus a, because proving it needs the compactness of the closed interval a to b, the Heine-Borel theorem. Okay, so this is a difficult proof. And of course, Heine-Borel theorem and compactness in general is already a difficult notion in elementary analysis. So it totally takes it's very natural to take some time to digest this. And lastly, we have the monster, the non-additivity proof. Right, so I got feedbacks from viewers that the first two streams are getting a little bit dense. Okay, and that's totally normal. It's not your fault as a beginner, but I'm just trying to say, when it comes to sigma algebra, we are starting from scratch now. Okay, so here, when we, right here, well, after we introduce sigma algebra, you can basically forget about the first section. The first section can be, I mean, they're important results, but you can think of real, not real, but measure theory really starts from sigma algebra. Shen has always wondered why the notion of countable union is considered the foundation in measures theory. I think so. I think so. The notion of countable union is absolutely crucial. So, for example, the third bullet point, countable union, the countable additivity. Why not closure under finite union, arbitrary union? It's a good question, because I think I answered that, right? Why is countable? Why is countable? Because we did an example some day ago. Sean, this is totally valid. Why not finite? So why not finite? This is we'll see that later. Okay, if you just have finite closure, let's say if you just have finite closure under finite union, and also only finite additivity. So imagine C, instead of having infinity on top, you have a little n, and the statement says the union of n disjoint subsets has an outer measure equals to the finite sum of the individual, not outer measure but mu value. Okay, so if you just replace the infinity sign by a little n, and at the end you say this is true for all n equals 1, 2, and so on, that would be finite additivity. The finite union, exactly, Vernon is very precise. This gives the notion so-called Jordan content, Jordan measure, quote-unquote measure. So we usually call that Jordan content. That's a different theory. So mathematical definitions are almost never made randomly. Here, because the main objective is to be able to swap integrals and limit. Okay, remember in chapter 1, that was a major reason why Riemann integral is considered insufficient. It's because Riemann integral does not behave well when you swap the orders of limits and integration. Right? So that's a very involved reason why we want not finite union. But why not uncountable? Well, that's actually quite easy, because we have, hang on, let me just find the notes there. So I made an example why uncountable additivity is a bad idea. Hang on. I really should organize my notes. That was the second stream where it got unfortunately cut short due to bad internet. So here's the answer here. Here we have a question. Question: is uncountable subadditivity possible? Right. Of course, subadditivity is weaker than additivity. If we don't even have uncountable subadditivity, then you can't have additivity, right? So yeah, go to the second stream for more in-depth. Actually, you know what? I should collect all these notes. I mean, as imperfect as they are, it's still perhaps worth looking at them. But anyway, so that's the counterexample. So you can consider the open interval 0 to 1 as the uncountable union of singletons x. Of course, this is an uncountable union. Right? So, of course, 0 to 1 has an outer measure of 1. But the uncountable sum, which is defined as the supremum of all the finite sums, okay, that's 0. So uncountable additivity fails. Okay, so yeah, very nice question by Sean. This is exactly the sort of question I wish to see more in chat. Of course, all the questions are great, right? But this is especially worth interrogating. Why countable measure? Because textbook usually just give the correct, quote unquote, correct definition, and then do deduction that way, right? But it may or may not address questions like, oh, why not finite union, or why not arbitrary unions? Okay, you want countable union because you want to be able to exchange limits and integration, and you don't want uncountable union because that's simply false. Okay, that's simply not what you want it to behave. Okay, anyway, so here we have, I was saying, starting from sigma algebra, this is a proper start of measure theory. This is a proper start of measure theory. So previously all the sections we did earlier tells you why you need to build a new house, why your old house might not be good enough, okay, why you need a new house. Here we laid the foundation of the new house. It started from sigma algebra. Okay, so starting from sigma algebra, pretty much everything is a fresh start. So it does not, here, for example, in the second section, it does not rely on your prerequisites that much. Okay, you just need to be able to follow some basic deduction. Okay, everything pretty much starts from scratch now. Okay, so here we have a simple property, some easy but important properties. Sigma algebras are closed under countable intersection. Okay, remember in the axiom or in the definition, we know that sigma algebras are closed under countable union. It is implied that sigma algebra also closed under countable intersection. Okay, so let's see how that's proved. First of all, what's the statement, and let's see how that's proved. Okay, suppose S is a sigma algebra on a set X, then X is in S. Well, this is already something we already mentioned. Here, B, if you have D and E in S, then the union of D and E, the intersection of D and E, and the difference set D minus E is in S. Okay, so that's nice. That's nice. So once again, in probabilistic language, what does A say? Imagine X is the sample space. Imagine X is a sample space. S is the collection of events. A says it says X itself is an event. X itself is an event basically means that's the event that contains all the possible outcomes. All the possible. So it's like when you imagine X is the set of head and tail. If you interpret X as an event, it means the coin is either a head or a tail. Of course, that's an event. It's always true. So that's A in probabilistic terms. Second, if you have two events, DE, then D or E, D and E, D but not E are all events. Cool. C says if E1, E2, blah, blah, blah is a sequence of elements of S, then their intersection is in S. That's actually paraphrased as the title of this result. Sigma algebra is a closed uncountable intersection. This is a countable intersection. Okay, so let's try to prove this. Okay, and typically this would require the usage of De Morgan's law. The De Morgan's law. We'll see how that's used. Okay, but first let's start from the easy ones. X is in S. This is because the empty set is in S, and X is the complement of the empty set. From the first two bullet points of the definition of sigma algebra, implies that X is in S, proving A. No issues at all. B, if D is in S, then the union of D and E is in S. So how do we do that? Well, of course, you need to use the countable additivity. Right? Sorry, not countable additivity. What's that called? Closure under countable union. Basically, the third bullet point. You want that. You want that? Okay. Actually, it might be just easier to say countable closure under countable union implies closure under finite union. Right? You can simply take the sets in the sequence E1 all the way in the sequence after a certain index, say n, the sets are all empty. So this way the countable union reduces to a finite union, and from closure under countable union you have closure under finite union. Okay, so that's the same. Okay. All right. So not sure would you remember this, but I once asked the geometry of ML irreducible error, and you made a video. Gave me so much joy. Oh, I think. Yeah, I think I remember a comment. Yeah, that's a few months ago. Okay. Yeah, no worries. Thanks for stopping by, Shan. Okay, so here we wish to prove C, right? Actually B, B and C. We said we wanted to just to use finite. What's that? Okay, sorry, I'm losing words. Closure under finite union. I wish there's a shorter phrase for that. Okay, it's not finite additivity because we're not even discussing measure yet. Okay, but basically the first statement, DE in S implies that D union E is in S. That's closure under finite union, because you can just treat D union E as a union of the sequence, D empty, and so on. Okay, okay, and what if you want intersection instead? Well, there's a nice interplay between union and intersection due to the De Morgan's law. So the De Morgan's law says the complement of the intersection is the union of the complement. Okay, so often in elementary courses on set theory, or even logic, we write it this way. So we write D intersect E, taking the complement, we use a almost like a complex conjugate notation. Equals to D complement union E complement. So there's a saying called break the line, change the sign. Refers to this particular notation. Break the line, change the sign. That's the De Morgan's law. Okay, so yeah, Captain Morgan guy sure is a logical pirate. I know, right? De Morgan, I wonder why does this name even have a name? Why does this result even has a name? De Morgan's law. I mean, with all due respect to the guy De Morgan, I'm pretty sure this is known before him, huh? Because this is so basic. I'm just surprised. I'm just surprised that this is even named after a person. Like, this is more basic than, say, the quadratic formula, no? But somehow the quadratic formula does not have a person's name attached to it. The cubic formula has a name, the Cardano's formula, even though it was discovered not by Cardano. But somehow this has a person's name to it. Like, anyway, we can live with that. So how does this help us? We wish to prove that if D and E is in S, then D intersect E is in S. Well, let's take a look at the right-hand side, shall we? Since D is in S, then the complement of D is in S. And the same can be said about the complement of E. Okay. On the right-hand side, we have a union of two sets in S. But we just mentioned S is closed in the finite union. So on the right-hand side, we know this is the set on the right-hand side. We know is in S. Actually, quadratic formula comes from algebra, and algebra is named. Yeah, I'm just talking about quadratic formula, the formula itself. Right? It's not named after a person. Yeah, De Morgan is from the 19th century. I know. De Morgan is actually is quite a prolific scholar. De Morgan was a collaborator of Stokes. Right? The Stokes theorem or Stokes formula from vector calculus. The two are collaborators, are colleagues. So De Morgan and Stokes together worked on subjects such as asymptotic analysis. Asymptotic analysis in astronomy and optics, I believe. So nowadays he's just remembered for this silly logic law, which is obviously known before him. Okay. I believe everyone knows De Morgan's law before him. Yeah, I'm just surprised like this is even named after a person. So yeah, where we're going. So yeah, it's probably about popularizing possibly a specific form. That's most likely the explanation. So you see, you don't need to be original to have a result named after you. Huh? But anyway, so on the right-hand side, we have a set that is in S. Okay, so this tells us what? This tells us the complement of D intersect E is in S. Well, the complement, taking the complement again, you get D intersect E. So therefore, D intersect E is in S. Okay, so it's not too difficult to show the finite intersection is closed in S. Yeah, quadratic equation. I think, yeah, quadratic equation comes from the Middle East, probably. Okay, I'm not a historian of mathematics, but I'm pretty sure the quadratic formula was discovered and well understood in the Middle East way before in, say, Europe. So anyway, here we also have the set difference d minus e. Right? The set difference can always be written as the intersection with a complement. So d minus e is defined as d intersect with the complement of e. So that's basically done. Since e is in S, the complement of e is in S, and we just proved that sigma algebra is closed under finite intersection. India too. Yeah, it's very old, possibly China as well. Yeah, so the Chinese developed Gaussian elimination, well, centuries ago before Gauss did. Of course, the Chinese mathematician, Chinese mathematics in general, prioritized practical calculation but not proofs. So there's that. So the level of rigor was completely different. Okay. Anyway, so here, for example, Chinese computed pi with great accuracy, but was not known for producing many elegant proofs such as Euclid did. Okay. Anyway, enough history of mathematics. Let's come back to this proof because this is a rather a basic proof, and it's a good practice when it comes to set operations. Okay. So De Morgan's law does not just work for finite operation. In fact, it works for arbitrary operation. I once violated De Morgan's law, ended up serving 5 years in solitary. Hi, Leo. Thank you very much for joining the stream. Here we have the final result, right? So, which is what this 2.25 proposition is about. Right? Sigma algebras are closed under countable intersection. And the proof for C is very similar to the proof of the second result in part B, closed under finite intersection. They're quite literally the same. Right? The steps are quite literally identical. So you can recall the De Morgan's law for countable operations. So it says the complement of a countable intersection is the union, is a countable union of complement. Okay, so in fact, the countability here is not even necessary. You can easily swap that to arbitrary union, arbitrary intersection. So basically, you inspired by a quiz question. I put up some questions, but only 2 now. Oh, that's great, awesome. I like those detours. Yeah, I know they're fun. I mean, I can't stop doing those myself, but I I try to keep up the pace. Anyway, we're not in any rush because we don't have like a deadline or some sort of exam at the end of the term, right? So we can be as thorough as possible. But still, I wanted to keep most things mostly concentrated on the main subject. So as you can see, the key is still De Morgan's law. On the right-hand side, what do we have? If you have E1, E2 all the way as a sequence of elements in S, then X minus EK are all in S for every K. And now let's use closure under countable union. The right-hand side is a countable union of sets in S, and therefore is a set in S. Therefore, the set on the left-hand side is a set in S. And then you take the complement of that, you simply get the countable intersection, the set that you actually care about. The intersection of EKs and S proving C. Okay, so the key is really just De Morgan's law. In fact, I think it's a good exercise. I think it's a good exercise that in the definition for sigma algebra, if you swap the last bullet point to be intersection, you can prove the third bullet point. So they're equivalent formulations. Sigma algebra is just group definition with union as composition with set difference as inversion. Is that though? I mean, it's always a good Thank you, George Pang from Hong Kong. So I don't think this quite work for abstract algebra. Sorry, I don't think this quite work for group. Is that though? Actually, I might be talking nonsense here. Let me just think. So if you think about S, if you think about S as equipped with a binary operation, union. So what do you need for the binary operation to satisfy the notion of a group? You need associativity. First you need closure, and you need associativity. You don't need commutativity, and you need the existence of inverse. Group compositions are binary. Yeah, of course, group compositions are binary. If you have associativity, then you can define things like A plus B plus C. This makes sense because of associativity. Of course, you start from a binary operation, and if you have associativity, then you can do operation with more than one argument. You need some notion of convergence. Yeah, so I was thinking perhaps 3 is a little bit difficult to incorporate in a strictly algebraic sense, no? In a definitional group, you don't have this closure unaccountable operation thing. But it's a good instinct, right? It certainly is a good instinct. Yeah, the group definition is a little bit ambiguous. Yeah, I would just perhaps it's nice to draw analogies, right? Because the name algebra is in the name. You can't help but think about abstract algebra and you think about this definition. But perhaps it's better just to treat it as it's a subject on its own, like a notion on its own. Okay, but always, I guess Leo, for example, knows a lot about category theory. I don't know how, because I'm very much completely ignorant when it comes to that. I don't know what would be the category theory perspective of sigma algebra. Yeah, so it's an F2 algebra with symmetric difference. Interesting. Yeah, so I was saying that you can swap the last bullet point in the definition of sigma algebra to be a closure unaccountable intersection and be able to prove the last bullet point. Yeah, a sigma algebra is not an algebra in the usual definition, right? What is an algebra even? An algebra, as far as I know, okay, is a special vector space. So if you can do vector multiplication and still get a new vector, that's an algebra, like a Lie algebra, right? So here you don't, perhaps Boolean algebra, because it's interesting to look at the name origin of this name. Why it's called sigma algebra? Sigma, okay, sigma has to do with countable union. Okay, this is something that we will see quite often later on. Okay, in measure theory, you often see this sigma something, like sigma additivity, sigma algebra, and sigma finite. Yeah, vector space with additional product. That's the algebra. Of course, you also have Boolean algebra, right? Anyway, so sigma always refers to some sort of countable operation, countable union, countable sum, that sort of thing. Right. So I don't know what the name where the name algebra comes from. Okay. There is such a notion called algebra, simply called algebra in measure theory too. So if you replace the last bullet point, which is countable closure under countable union, by closure under finite union, that's called an algebra. Yeah, algebra is a highly overloaded term, so it's difficult to, perhaps it's difficult for me, but there's got to be some reason how the name sigma algebra sticks. Also, okay, just to make things extra confusing, it's also in some books called sigma field. So sigma algebra is sometimes also called a sigma field. Once again, you might be tempted to think about, oh, the field in algebra. But of course, this does not look like the field at all. So I have no clue why it's called a sigma field. Okay, just treat it as some buzzword. Okay. But we know why this is introduced and what does it do. So that's enough. Potato, potato. That's how I like to think of it. So if deeper connections do show up later, of course, this is much appreciated, but it's not necessary. A single explanation as simple as mathematicians being human. Okay, fair enough. All right, so yeah, this is a simple proof, so I will not reproduce it in my notes. But basically, it's a good practice, by the way. It's just that I wanted to get the move on. Okay. Next definition. Now we have the notion of so-called measurable space. By the way, later on we will see a notion called a measure space. Measure space. The measurable space and measure space are different notions. Okay, so you can think of measurable space as a space that is ready to assign a measure to it. It still does not have a measure, but it is ready. Okay, it's called measurable space. A measurable space is an ordered pair, X and S, where X is a set and S is a sigma algebra on X. Okay, an element of S is called an S measurable set, or simply a measurable set if S is clear from the context. So this is called an S measurable set. An element of S is called an S measurable set. Or simply a measurable set if S is clear from the context. So that's an important definition. Why don't we just put that down? Definition. Let X be a set, scripted S be a sigma algebra on X. Okay, so the ordered pair Sx together is called a measurable space. And not a measure space, which will be introduced later. Okay, if E is in scripted S, E is called a S measurable set. Or simply measurable set if S is clear from context. I call myself an algebra, or probably algebra-er. I invented that word, prefer to over algebra. Okay, anyway. So here, that's the new notion we introduced today. For example, if X is real and S is the set of all subsets of R that are countable or have a countable complement. Well, that's basically one of the examples we did earlier. Here, the set or the collection of subsets that are countable or have countable complement form a sigma algebra. So here we have, for example, if X is real and S is a set of all subsets of real that are countable or have a countable complement, right? Then the set of rational numbers. The set of rational numbers is S measurable. Why? Because the set of rational numbers Q, the set Q of rational numbers is countable. and therefore Q belongs to S, and therefore it is S measurable. It's just different names being thrown around to mean the same thing. Okay. But the set of positive real numbers is not as measurable. So basically 0 to infinity is not as measurable. Why? Well, because 0 to infinity is not countable, its complement, which is minus infinity to 0, is not countable either. So it's not in S, and is therefore not as measurable. Okay, just to practice the definition here. Okay, and now let's get into a super duper important notion called the Barreal subset. This is the most important sigma algebra. So there's the notion of so basically in our applications, in, for example, statistics, 99% of the sigma algebra you encounter is so-called Barreal sigma algebra. It's always funny when you spend weeks studying math only to learn in the end all these definitions are redundant and equivalent. Well, it's not a waste of time. It's not a waste of time because sometimes the equivalence of definitions themselves are important theorems. The equivalence of definitions is not always trivial. Okay. Sometimes, of course, crucial flow research. Sometimes we do need to spend quite some time trying to navigate literature, because in literature sometimes people might use different terms to mean the same thing, and it is an important skill to be able to recognize them, because this is just a way that not all fields are completely standardized, right? It's not a it is funny. It's not a waste of time. Yeah, I get it. So it comes down to two things. One is develop the skill of navigating literature. Sometimes people say different words, but to mean the same thing. That's one thing. And the second thing is there might be different perspectives to define the same notion, and that's actually hugely enlightening. Actually, guys, my favorite theorem, actually my favorite type of theorem, are as follows. I'm not sure if you guys have the same feeling. My favorite type of theorem are the following are equivalent, TFAE. So it's usually the equivalence of several definitions. And I particularly like this sort of thing. In particular, in linear algebra, there are so many different characterizations of invertible matrices, for example. I love this sort of theorem, because this means you can think about a notion from so many different angles, and for different problems, usually there's a most convenient way to think about a certain object, right? So yeah, so sometimes when you deal with invertible matrices, you want to think of them as matrices whose columns are linearly independent, square matrices whose columns are linearly independent, and sometimes you want to think of them as matrices whose determinant is non-zero, blah blah blah. What about your least favorite theorem? My least favorite theorem would have to be it's hard to say, right? Because it's if something is called a theorem, there's typically something non-trivial about them. But basically, I would say my least favorite theorem are some sort of existence uniqueness theorem in differential equations. I know they're important for practical purposes, like in applied mathematics, when you formulate a problem as a differential equation, dynamical system, and whatnot, you need to prove existence of uniqueness, right? But generally speaking, those theorems are almost always sufficient but not necessary conditions. In my opinion, that can be a little bit disappointing, but Anyway, just from sheer elegance perspective, I don't deny their practical usage. And the hypothesis tends to be very long. There's a lot of hypotheses. Just for example, I was still debating. I'm still debating because I have a series on stochastic calculus, right? I'm still debating whether or not to make a video on the existence of uniqueness of solutions of SDEs. Once again, at a non-measure theoretic level. So I was still debating that because I mean, on one hand, it's a nice application of the contraction mapping principle, the Banach fixed point theorem. But on the other hand, the theorem is such a tedium to state. Okay, yeah. Anyway, let's keep going. Barreal sigma algebra, Barreal subset. Barreal subset. Okay, so the next result guarantees that there is a smaller sigma algebra on a set containing a given set A, scripted A, of subsets of X. Let's read this sentence a bit more carefully. What are we doing here? Always skip existence uniqueness of OD, but begin to appreciate it finally. Yeah, they're important, of course. They are extremely important because if you don't have existence uniqueness, well, the problem, first of all, is not well posed, and numerical simulation might even give you nonsense. Right? Think about the Navier-Stokes problem. Right? Navier-Stokes existence, uniqueness, and smoothness. Of course, that's tremendously important. It's just, oh my goodness, when I was studying the qualitative ODE, there's just so many different versions of existence uniqueness theorem. Of course, they are. It's necessary. You need to deal with them in applied problems. But man, are they boring to state. Anyway, here we have this particular little proposition called the existence of smaller sigma algebra. Okay, so imagine this is a situation, right? You have a set X. Let me just draw a Venn diagram, X. Okay, and there are certain sets in X that you're particularly interested in. There are certain subsets of X that you're particularly interested in. They don't have to be disjoint or anything. It's just there are certain classes of X, certain classes of subsets of X. My goodness, that's difficult to that's mouthful to state. Basically, in a set X, you have certain classes of subsets that are particularly well understood. For example, on the real line, open intervals are well understood. You like those sort of things. And you want your sigma algebra to contain those. Of course, not every sigma algebra contains them because, as we just saw, the smallest sigma algebra only contains X and the empty set. I mean, it is a sigma algebra, but it's pretty useless. Right? We want our sigma algebra to contain sets that we understood or what we already understood. So here's the problem. You have a set X and you have a given set or a given collection of subsets called scripted A. And we wonder if there is a sigma algebra that contains A. Of course, there is, right? There must be a sigma algebra that contains scripted A because you have the biggest sigma algebra, the power set. The power set contains all possible collections, scripted A, of subset of X. But once again, we don't want that big either. Right? So you see, this is the idea. We want a sigma algebra that contains certain interesting classes of subsets, but we don't want the power set either. So here's the proposition. X empty is pretty useless. That's sigma algebra. I don't mean to shame, right? Yeah. I don't mean to shame this result because it can be used as a common, used as a nice example to create things like counterexample. So, yeah. Of course, trivialities do matter, but for practical purposes, you don't generally work with X empty. So here we have the notion of smaller sigma algebra contain a collection of subsets. Yeah. So suppose X is a set and scripted A is a set of subsets of X. then the intersection of sigma algebras on X that contains A is a sigma algebra on X. So what is going on here? Let's consider a sigma algebra. Let's consider a sigma algebra that contains A. Right? Such sigma algebra must exist, the power set. So therefore, we can collectively think of the sigma algebra that contains A as a family of sigma algebras. And then you just take the intersection of all of them. The intersection of all of them guarantees this is the smallest sigma algebra. So that's how you get the smallest sigma algebra. So let's consider a parallel result in linear algebra. Okay, this is a side tangent, but helps to secure the intuition here. So imagine, recall in linear algebra, what is a span? What is a span in linear algebra? Let V be a vector space. Doesn't matter what sort of vector space. It's just a vector space. Let V be a vector space, general vector space. Okay. Let V be a vector space and let S be a subset of V. What is the span of V? What is the span of S? The span of S is defined as the smallest subspace. Defined as the smallest subspace of V that contains S. Okay. So how do you show such thing even exists? How do you show such thing even exists? Well, proof of span of S exists. Prove that span of X as exists. Well, what do? You consider the collection of all vector spaces that contains S. Consider, say, okay, this is terrible, but okay, consider V as the collection of U subspace. U is a subspace of big V such that U contains S. Okay, this is a non-empty collection. Is not empty. Since big V itself is in it. Since big V itself, that's not an empty set. And now you can just define, okay, and you can just define a claim, the span of S is their intersection. Is the intersection of all the subsets in big V. This is because the intersection of subsets is still a intersection of subspace is still a subspace. So this is, the right hand side is guaranteed to be a subspace. It's guaranteed to be the subspace. And how do you prove the smallest part? Right? We show this is a subspace. Right? On the rest, this is a subspace because the intersection of subspaces is still a subspace. But What about the smallest? How do we even formulate the smallest? Okay, 1 is a subspace since subspaces, can you say subspaces is closed? No, you cannot say that, since intersections of subspaces is still a subspace. I remember doing this proof in one of the Loomis and Sternberg live streams, which was several weeks ago. And also, the intersection of big V contains S. Okay, how do you argue the smallest part? Well, you suppose, say W is a subspace, of V, and W contains S. And you want to show that W is contained in the union. Need to show W contains, sorry, not the union, but the intersection of big V. So that's basically the smallest part. This is the smallest part of the claim. Okay, and once again, this is left as exercise, just like at the intersection of all subspace is subspace. Right. So it's very similar to how sup and inf are defined, right? So sup and inf, for example, inf is lower bound and is the greatest lower bound. If something else is a lower bound, the inf must be greater or equal to it. Also, if people want a category theory, is an example of such thing called a junction. Thank you very much. Leo, are you a category theorist or algebraist? I noticed you have stuff on your channel that are has to do with some quite deep abstract algebra stuff. I have a lot to learn from you, actually. So that's basically the sketch of the proof of span exists. Sup and inf also example of a junction. Yeah, I have this feeling, right? This kind of like the logic of sup and inf. Anyway, here it's coming back to measure theory. The proof is pretty much a verbatim adaptation of what we just did in linear algebra. So here we just consider all the sigma algebra that contains A, and just take the intersection of them. That becomes the smallest sigma algebra. Let's read the proof. There is at least one sigma algebra on X that contains A, because the sigma algebra containing all subsets of X contain A. So that's the biggest sigma algebra, the power set Px. Px contains A. Okay. So once again, these are deeper understanding. I mean, to follow these results, you just need to be able to follow set inclusion arguments. So it's pretty straightforward. Okay. Let S be the intersection of all sigma algebra that contains A. S, you see, this is the intersection of all sigma algebra of X that contains A. Right? We need one thing. The all sigma algebra of X is a non-empty collection. All sigma algebra on X that contains A to be a non-empty collection. This way you can take the intersection. That's the first paragraph. That's the purpose of the first paragraph. So S is now the intersection. And now it's just a matter of verifying the three sigma algebra axioms. That'll be it. Okay, so Here, empty set is in S. Complementation is closed in S. And finally, the countable union. Countable union is also closed in S. Okay, so actually, I would argue it's probably better to also include the smallest part, right? Because here, 1, 2, 3 verifies that S is a sigma algebra. This proves S is a sigma algebra. But how do you know this is the smallest? The smallest coming from the intersection. So you need, in my opinion, right? It's better to also supply the smallest part. So here, using the terminology smallest for the intersection of all sigma algebra that contains a set scripted A of subsets X makes sense because the intersection of the sigma algebra is contained. Right? The intersection of the sigma algebra is contained in every sigma algebra that contains A. Yeah, I would probably add this sentence into the proof. By the virtue of being the intersection of all sigma algebras that contains A, it is the smallest sigma algebra that contains A. Okay, so there's that. Okay, so we're going to apply this result, 2.27, to the situation where A is open set. Right? A is an open set on the real line. Okay, so here, actually, you know what? Let's take a look at the examples here. Examples of smallest sigma algebra. Suppose X, my book has a chapter on categories here. Crucial flow. Actually, you know what? If you want to, you can post the name of your book in the chat and perhaps in the Discord server as well. Okay. So a lot of people are interested in category theory and quite knowledgeable about them. So actually, I mean, at this point, I mean, I've heard of it in grad school, but I'm pretty much illiterate. Okay, so yeah. Anyway, let's continue. So 2.28, smaller sigma algebra. That X is a set. Suppose X is a set, and the scripted A is a set of subsets of X that consists of exactly one element. So scripted X is an arbitrary set, and A is the collection of singletons. Okay, no worries. Yeah, no worries. Everybody can have their own publishing standard. Yeah, if like, I suppose by writing a book, the goal is to eventually communicate it present it, right, with the rest of the world. But there's absolutely no pressure. I'm not I'm just because we're interested in other people's work and we're interested in other people's knowledge, but it's totally voluntary. Yeah, and it's just probably if any tutorial on category theory is very likely to be above my current level, but I'm still interested. Okay. Anyway, so here, scripted A is the collection of all singletons. When we have this collection, how can we describe, or can we even describe? Can we describe the sigma algebra that contains A? Here you have a collection of subsets of X. First of all, A itself is not a sigma algebra. This is obvious because, well, by taking the intersection of two distinct singletons, you get the empty set. You get the empty set, which is not in A. Right? So here you have a collection which is not in itself a sigma algebra, but you can always find a smaller sigma algebra that contains it. So here, how do we describe the sigma algebra? We call it in probability theory, we call it the sigma algebra generated by A. We call it the sigma algebra generated by A. So here we have a collection of A. I'm actually going to use this terminology. Okay, I'm going to the smallest sigma algebra containing A. It's because this is a long phrase, right? We're going to use the notion of sigma algebra generated by A. Let's write that down. Okay. 2.27. 2.27, smallest sigma algebra. A collection of set. Okay. Suppose X is a set and A is a set of subsets. So we just write A is a subset of Px. Then let's write it as sigma A, because this is quite common notation in probability theory. Even though I'm not sure, okay, this is a standard terminology, standard notation, scripted A, sigma of scripted A. My grad advisor write it this way. Basically, this is defined as the intersection of all sigma algebra on X such that containing, let's say, containing A. Okay, so this is the smallest containing A. Okay, so that's the proposition. So you know what? For the sake of practicing the definition of sigma algebra, let's redo the proof. Even though this is not that difficult. Okay, and we say this is also, we call it the sigma algebra generated by A. Kind of like the span. Can you imagine every time you say span, you have to say something like the smallest subspace of S that contains S? That will be multiple, right? The sigma algebra generated by A. Okay, let's do the proof. Of course, um, it suffices to prove that sigma is indeed a sigma algebra. One. Okay, the empty set belongs to sigma of A. Okay, so how do we prove that? Well, this is simple because every sigma algebra on X containing A contains the empty set, and we're done. 2. Then we need to prove closure under complementation. Suppose, well, actually, let me just add one more sentence here. Because the intersection needs to be taken over a non-empty family. There is at least one sigma algebra on X that contains A. That is the power set of X. Okay. The second, so let's suppose E is in sigma of scripted A. Okay. Then, because of sigma is defined as the intersection, then E belongs to every. Then for, let's say, for every sigma algebra S on X that contains A, E is in A. E is in S. E is in S. Okay. So this means X minus E is in S. The complement is in S. Once again, for every such sigma algebra, and therefore X minus E is in the intersection of all of those S, which is exactly the sigma algebra generated by A. Okay. Third one. Suppose you have a sequence E1, E2, and so on is in sigma of A. Okay. So then for every sigma algebra on X that contains A, you can follow this. For every such sigma algebra, it contains the entire sequence. E1, E2 all the way is in scripted S. X, we need to show what? We need to show the countable the union is in S. So the countable union of EK is in S. And therefore, the union of EK is in the intersection of all the S, which is equivalent to the sigma algebra of A. Sigma algebra generated by A, so we're done. All three axioms are verified. Okay. Simple proposition, but it's good practice to internalize the definition of sigma algebra. And here we have the examples. The first one, it says, let's consider A to be the set of subsets that consists of exactly one element. So A is a collection of all singletons. These streams return me to the feeling of studying analysis with classmates at the whiteboard. Yeah, exactly. As I was saying, this is not a series of lectures, okay? It's rather a seminar. It's exactly supposed to be that kind of feeling. You study with a group of classmates, okay? I'm your classmate. Everybody in chat is your classmate. There's no professor, just a bunch of people with a text and perhaps papers. Okay. Anyway, so here we have a collection of singletons, and we want to describe the smallest sigma algebra generated, or just the smallest sigma algebra that contains scripted A, or the sigma algebra generated by scripted A. How do we describe that? Here, it says the smallest sigma algebra on X containing A is the set of all subsets E of X such that E is countable, or X minus E is countable, as you should verify. Okay, so we have to do it ourselves. Okay, example. Smallest sigma algebras. Okay, example 1. Let X be a set. Scripted A is the collection proved by delegation, by relegation. I think this is something Folland. You guys know Folland? Folland is the author of the most popular, possibly the most popular textbook on measure theory. It's called Real Analysis, Modern Techniques. Right. So this is probably the standard book in grad school. He said something in the preface called "When in doubt, left as exercise," to avoid quote-unquote verbosity. Isn't that guy on Norway Folland? Okay, I have no clue. Okay, yeah. So Folland has this habit of leaving a lot of exercises in a text, just to avoid redundancy. The book is not very long, as far as by the considering the content it contains, but it's certainly very terse. So here, A is the collection of all singletons in X. So A is defined as singletons X such that X is in big X. Okay, show that sigma algebra generated by A is the set E, subset of X, such that E is countable. Or X minus E is countable. Of course, we already seen this is a sigma algebra. Right? We already seen this is a sigma algebra. But how do we show this is the smallest sigma algebra generated by A? Or just sigma algebra generated by A? So yeah, this is an interesting exercise. Well, we know the right-hand side is a sigma algebra. Let's just give it a name. Okay, call it scripted S. So scripted S is already known to be a sigma algebra. Okay, let's just quote the relevant number so that we don't get confused later when we read our own notes. So that's example 2.24 bullet point 3. So this is a sigma algebra. So we need to show something. First, it contains A. So we need to show 1 scripted S contains A. And what about the smallest part? How about what is the smallest sigma algebra of all the singletons except exactly 1? Huh. Yeah. Okay. Here, let's work on this one. So 1 is A is a subset of S. Okay. And second, we need to show the smallest. How do we show the smallest? Well, we show that, suppose let's call it T. So, okay, T is a sigma algebra, or not suppose, but if T is a sigma algebra on X that containing scripted A, then S being the smallest means S is contained in scripted T. So we need to show these two parts. So this way S is the smallest. Okay, so start with 1. Okay, let E belongs to A. The simple element chasing argument. So let E belong to A. Then E is a singleton. And E is a singleton, so, well, E is countable. So E is countable, and therefore E is in scripted S. Okay. So therefore, A is indeed a subset of scripted S. So that's easy. Okay. 2. So suppose you have a sigma algebra on X that contains A. You want to show S is in T. Because this is our hypothesis. So let E be an S. Let be an S, you need to show E is in T. Need to show E is in T. So how do we get around that? Well, T, as we said, is the, hang on a second. T is a sigma algebra that contains A. S is a sigma algebra that contains A. No. Yeah, S is a sigma. As we said, S is therefore we'll just say therefore S is a sigma algebra. Why is this the smallest? S is a sigma algebra on X containing A. We need to show S is the smallest. So we suppose T is a sigma algebra on X containing A. We need to show S is containing T. So starting from an arbitrary element E in S, we need to show E is in T. Well, let S in E, so let's work from here. So you have E is countable or E is X minus E is countable. So let's do cases, okay? Case E is countable. So E is countable, therefore E can be written as a list. Can we write E as a list? Write say x1, x2, and so on as an enumeration of E. So that's the enumeration of E. Why this is in T? Remember, T is a sigma algebra that contains A. We don't know whether the elements x1 all the way to x1 blah 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 are in A. No, we don't know that. E is in S. E is in S. Are the elements here necessarily in A? No, not really. No. How do we show this is? Okay, so what does E in T mean? What does E in T mean? T is a sigma algebra on X that contains A. Guys, I'm stuck. So it looks like I'm stuck. So we managed to show the obvious stuff, right? So S is a sigma algebra on X that contains A. We need to show this is the smallest. So I pick an arbitrary sigma algebra T, want to show that S is contained in T. But by assuming E is in S, we can conclude E is countable or E has countable complement. So start with the first case, E is countable. If E is countable, then E can be written as a list. If you construct sigma algebra, Renan says, if you construct sigma algebra containing A from bottom up by transinduction. Okay, how far do you need to go? Okay, I'm just saying for this question, can I perhaps use, if let's say you have E1 all the way to En as an enumeration of E, how can you work from there? Every sigma algebra that contains A. Is there any hint in X? Or do we use the idea of the proof, taking the intersection of all the sigma algebras containing A? Hmm. So what do we manage to show here? In point one, S we know already is a sigma algebra. This is a sigma algebra containing A. So sigma A is a subset of S, no? Because sigma A is defined as the smallest sigma algebra that contains A. So S is a sigma algebra. So here you have sigma scripted A. Sigma of scripted A is a subset of S. So you have that. Do we have the opposite? We have the opposite. So yeah. So let's modify what we need to show. Show sigma of A is contained in S. Okay. And 2 is the opposite. 2 is the opposite. So can we write it as S, shall we say, sigma A contains S? Can we do that? Well, if let's say S is the S S is this thing, right? S is the set of S is the collection of countable sets and sets whose complements are countable. I think it has to do something with this one, right? So if you can consider two cases, right? Here you have E in S, right? So E is either countable or have countable complement. If E is countable, then E can be written as a countable union of singletons. So which are countable unions of sets in A? The singletons are in A. And by closure under countable union, the countable union is in sigma A. Hmm. So how do we actually, let me just erase that. I think I'm on the right track, but I'm still struggling to connect the dot here. I want to show that S is contained in sigma of A. So how do we go about showing that? we need to show, okay, let's rewrite this. We rewrite this as such. So here let S E be an S. You need to show E is in sigma A. Let's do two cases. Case 1, case E is countable. E is countable, therefore E is a countable union of singletons. But what does that mean? If it's a countable union of singletons, i.e. E is a countable union of sets in A. Right? Sets in A. So E is a countable union. E is a countable union of sets in sigma A. Which of course belongs to sigma. Belongs to sigma A. Okay, so yeah, that's the full argument. So if you have E is countable, then E is a countable union of singletons. Okay, because singletons are all in A, E is a countable union of sets in A. And because sigma A contains A, E is a countable union of sets in sigma A. By the virtue of being a sigma algebra, E is in sigma of A. So that's exactly what we wanted in the first case. Second case, E is not countable. Okay, I haven't paid attention in chat, but yeah. So sorry guys, I was just too focused on the problem. But basically, yeah, that I think that should be the correct argument. So case E is not countable. That must mean E is X minus E is countable. But then again, you can apply the same argument. By the same argument, X minus E is countable, therefore X minus E is a countable union of singleton. And blah blah blah, X minus E, using the same argument. You have X minus E is in sigma A. Okay, X minus E is in sigma A, and by the virtue of being the sigma algebra, E, which is X minus E, is in sigma of A as needed. So we're done. So we have the opposite direction. Therefore, sigma scripted A contains scripted S. So we're done. Okay. Hi, cat. Yeah. All right. So that took longer than expected. Second one. Suppose A is of just two sets, 0 to 1 open interval, 0 to infinity open interval. Then the smallest sigma algebra on R containing A is the following, as you should verify. Wow, this is interesting. You now have an explicit construction. So let's write that down. What do we want? Second example. So X is R. Scripted A is just two sets, 0, 1, 0, infinity. Right. So show that sigma of scripted A is the empty set. Right? Of course, it always has the empty set. 0, 1, 1 to infinity. So this is A. Sigma algebra is generated by A, of course, contains A. And then you got minus infinity to 0, union 1 to infinity, okay, and minus infinity to 0 itself, okay, 1 to infinity, and what and also you have minus infinity to 1, open interval, and R itself. Okay, so we wish to show that. I guess the hierarchy rule might be fruitful here. Not sure what that means, but anyway, let's just continue with the exercise proof. So, all right. So there are certain elements that are obvious, right? So there are certain elements. Empty is obvious. R is obvious. Elements in A are obvious. So we just okay. So first we need to show this. The other three. The other three must be in every single sigma algebra that contains A. And perhaps also need to show nothing more is needed. So here you have an example of a sigma algebra being a finite set. So this is an explicit construction of a sigma algebra. Okay. Right, see you, Leo. Thank you very much for joining the stream. Thank you very much for your input. Leo is very knowledgeable. So guys, if you haven't subscribed to Leo's channel, go ahead and do that. Especially if you're interested in abstract algebra and category theory and number theory and all sorts of things. All subjects that I'm very much ignorant about. Okay. Thank you very much for joining my stream. Okay. So here we have you need to show the three that aren't completely obvious. Yeah, by the way, Leo, I saw you did like co-stream, if you can call it that way, with some other creators. I'll be honored if you wish to do one with myself, okay, with me, okay, if that's something that you're interested, just say, okay. So here you have these four sets that we need to show is in the sigma of A. So here, what do we have? So the first one, minus infinity to 0, obviously this is needed because that's the complement of 0 to 1. Is R minus 0, 1. So this is needed. Okay, that's it. And minus infinity to 0, that's the complement of 0 to infinity. Okay, and what else here? 1 to infinity. Well, 1 to infinity is the difference of the first two. Is the set difference between the first two. Okay, so there's that. And which one? Minus infinity to 1. What is minus infinity to 1? Well, minus infinity to 1 is the union of minus infinity to 0 and 0 to 1. Okay, so these are all needed in any sigma algebra that contains A. In any sigma algebra that contains A. But how do we show this is the smallest sigma algebra? Well, we just need to show this is a sigma algebra. That's it. Guys, is my argument correct? So here we show that every sigma algebra that contains A needs these 4 sets, in addition to the obvious one, empty, the sets in A, and the whole set. I claim that to show this is the smallest sigma algebra contains A, we just need to show this is a sigma algebra. Because you cannot delete anything from there. So this is the smallest. So it remains to show guys, here. Yeah, I'm back. Okay, sorry, bad internet again. Seems like something that happens at least once during every stream. Okay, so because this is a finite collection, so you just need to show it is closed under pairwise union. Okay, so showing this is a sigma algebra amounts to verifying the axioms, right? So you have the empty set in there, and you have closure under complement. Closure under complement is just a matter of enumeration. You just check the complement of each set is in the collection. So that's also pretty straightforward. But the last point, closure under countable union, requires some justification. So because I would like to claim that if you have a finite collection, then union, the closure under pairwise union. Guys, can you hear me? Just finish this sentence here. Okay, so we'll prove this. Okay, we'll prove this. So basically, I'm claiming that you just need to check sigma A. This set is closed under finite, or not finite, but pairwise. Not just finite, just pairwise union. That's already enough. Okay, we'll come to this proposition and we'll prove it. Yeah. Okay. All right, guys. Just want to say hi and thanks. Thank you, Alien. I'm working through the last stream. Hopefully this one goes well. Yeah, I know. Yeah. Yeah, sorry about the interruption. There's really not much I can do about it. Okay, so let me just finish this example as well as the proposition. I mean, the example relies on this proposition. So one empty set is in sigma of A, that's already done. 2, you need to check complement. So check complement. Why don't we just do a table here? That should be straightforward. So you have empty set. This is, let's say this is E. Okay, this is X minus E. Empty set 0, 1. 0, infinity, 0 to infinity. Minus infinity to 0. Union 1 to infinity. Minus infinity to 0. 1 to infinity. Minus infinity to 1. And real. So I didn't do anything super important. Okay, it's just a matter of checking a closure under complement, which is easy. And now I'm just going to make a big table here. My goodness. I don't need this. Okay, so I'm just going to make a big table to check complement, so not complement, but union is closed pairwise. Okay. Anyway, did everyone leave? I don't blame you because this is super annoying. But I'm just going to keep going. It doesn't matter. I mean, I do this on my own, so internet connection is a non-factor. Empty 0 to 1, 0 to infinity, minus infinity to 0, union 1 to infinity, minus infinity to 0, close interval, 1 to infinity, close interval, minus infinity to 1, open interval, and R. Yeah, I keep going, of course. It's just like one of the things, one of the crosses we bear living in Canada. Terrible internet for horrendously high price. What can you say? All right, so let's take the union. Of course, the diagonal elements are super easy. Actually, the first row is just union with the empty set. Okay, it's kind of tedious, let's be honest, but let's just be safe. Check all the pairwise possibilities. And then we prove this little proposition at the end to secure the whole argument. All right? Okay, so here you have 0, 1, 0, 1. 0 to infinity. Okay, this is R minus infinity to 1. 0 to infinity. Minus infinity to 1. Real. Okay. Zero to infinity. 0 to infinity, 0 to infinity, real, 0 to infinity, real. Okay. Okay, and this is real. Hold on a second. What's going on here? Oh, actually, I copied it wrong. This should be a closure. This should be a square bracket here. Yeah, otherwise if it's open, then union with this one gives you R minus 0. That's wrong. So here, R. That's just itself. Okay, and here you have itself again. Itself. Okay. Then that's R, and this is R. Okay. This is R. Okay, and minus infinity to 0. It's a grind, guys. And lastly, same as earlier. Oh, actually, no, this is wrong. Just minus infinity to 1. Real. Okay. 1 to infinity. 0 to infinity. 0 to infinity. This is closed. My bad. I keep making the same mistake. Should be closed. Okay, and here should be minus infinity to 0, the two-part set. Okay, and this is 1 to infinity. This is real. This is real. Okay, almost there. Minus infinity to 1. Minus infinity. So this is minus infinity to 1 again. Oh, actually, it should be closed. Hold on a second. This should be open. Open, open. I appreciate the detail, complete, and not boring. Yeah, thank you very much. Yeah, it's a grind, guys. So checking the union. Well, Axler left the exercise to the reader. If I just leave the exercise to you guys, then I'm just reading the text verbatim. Now, what's the point, right? So, okay, here you get real, here minus infinity to 1, minus infinity to 1 again. Oh, actually, you know what? Oh, this is R. This is R. No, minus infinity to 1. Finally, R. So the point is, in this gigantic table, every set as an outcome of the union is in this set. Okay. R. Okay, the last row is super easy. Everything is R. Okay, so now it's just a matter of verifying the last proposition, and this is quite productive because the last proposition is quite general. Once we have that, we can use that for all finite collection. Right? If you want to verify a finite collection of sigma algebra, you just need to check 3 things. It contains the empty set, it's closed under a complement. Right? So these are the original sigma algebra axioms, and the third one can be replaced by closure under pairwise union. You don't need to check countable union anymore. So that's nice. So now let's try to prove this result. Okay. So here, let's try to prove this result. Basically, you have a finite collection. So let's let S to be E1 all the way to En. Be a finite collection. of subsets in X. Right? So we suppose this is closed under pairwise union. Suppose for all ij in the set 1 all the way to n, ei intersect each union ei union ej is in X. Right. And now we need to show closure under countable union. So let say fk k greater or equal to 1 be a sequence of subsets, or just be a sequence in S. Okay, be a sequence, and we want to show that you need to show it is, or I mean, it is a sequence in S, so therefore there's only distinct, at most, distinct n elements. The sequence can involve, so that's the main argument here, can involve at most n distinct sets. So therefore, the union of fk, k from 1 to infinity, this is just the union of, you can write it as, perhaps let's use a, I from 1 to m, where I1 all the way to IM are distinct. And of course m is less than or equal to n. So you can just use the pairwise closure repeatedly. Use the pairwise closure repeatedly, and you get A1 union A2 is in S. A1 union A2 together union A3. Of course, the bracket does not matter. I'm just saying we're using the previous outcome, okay, previous result here, and blah, blah, blah. So, and so on, you get the union of I from 1 to m belongs to S. So we're done. This is a little proposition. Okay, so this tells us that for finite collection, to verify countable union is closed, you just need to verify pairwise union is closed using this giant table. Okay, so let's continue. So now we come to a crucial definition. We're finally ready to talk about Barreau set. Okay, the smallest sigma algebra on R containing all open subsets of R is called a collection of Barreau subset. An element of this sigma algebra is called a Barreau set. What do you mean you can't see me? See me as a like my face? I didn't put up a webcam. Can you see the screen? You should see the definition of a Barreau set. Zigzag. Do you see the definition of the Barreau set on the screen? Can everyone see the definition? Let me just check my... You can only hear your voice. Am I not sharing screen? The hell? I'm sharing screen. I can't see it on my end. What's the point of this? What's the point of... We're learning measures theory. That's the point. If you can use an LLM to prove the content, what? Okay. Anyway, doesn't matter. Okay. I don't know what you mean. Okay. So here we're seeing the definition of Barreau set. This is a crucial definition because in most applications we deal with the definition. We deal with Barreau subsets. Okay. In, for example, statistics, we deal with Barreau subsets. Okay. So here the Barreau subset is simply the sigma algebra on R that contains all open subsets of R. So just to remind ourselves, what is an open subset? Open subset of R. So just briefly remind ourselves, E in R is open if every point in E is an interior point. If for every x in E, okay, for every x in E there exists an epsilon greater than 0 such that x minus epsilon, x plus epsilon is contained in E. So the idea is every point in an open set has some sort of wiggle room. Okay, you cannot just move x by a little amount and immediately falls out of the set. It cannot happen. Okay, every point in an open set is interior, meaning every point has a little bit of a wiggle room. So these are the open sets. Of course, open intervals are open sets, but open sets aren't just open intervals. And we consider the sigma algebra generated by, or the smallest sigma algebra containing all the open sets, right? Barreau sigma algebra. Barreau sigma algebra is the sigma algebra generated by open subsets of real. Okay. So that's the definition of Barreau set. Of course, if you guys know topology, the notion of open sets can be generalized to topological spaces. Right. So if you have a collection of open sets, right, if you have a collection of open sets, but basically in topological spaces, open sets have their own axioms. Okay, which I will not state here, is irrelevant. But basically, you can talk about open sets in general topological spaces. And as a result, you can talk about Barreau sets on topological spaces. So R is an example of a topological space. So the notion of Barreau subsets is actually quite general here. Okay, so here it says we have defined the collection of Barreau subsets of R to be the smallest sigma algebra of R containing all the open subsets of R. We could have defined the collection of Barreau subsets of R to be the smallest sigma algebra on R containing all the open intervals. Okay, we could have defined it to be the smallest sigma algebra containing all the open intervals. Okay, open sets and open intervals aren't the same, but every open set on R is a union of sequence of open intervals. So what it's saying is every open set of R is a countable union of open intervals. This is a standard result from basic real analysis. Every open set of R is a union of countable open intervals. So basically, open sets on R can only look like this, and so on. Okay, so that's a nice little result. But in general, Barreau subsets. But this result is peculiar to R. This result is peculiar to R. For example, in R2, you do not have this situation. Do not have an analogous result. So in general, we define Barreau sigma algebra as the sigma algebra generated by open sets. Okay. Actually, you know what? I took back what I said. In R2, you would use open balls instead of open intervals. Open intervals in R1 is essentially open balls, right? Open balls. These are x minus epsilon and x plus epsilon. These are open balls. I think in R2 you can also talk about open balls. You can also say the Barreau sigma algebra on R2 is the smallest sigma algebra containing all the open balls. That works too. Yeah, that works too. So, yeah, it's in topological spaces where you don't have the notion of open balls that you have to speak of generated by open sets. Okay, but anyway, so here let's look at some examples. Every closed subset of R is a Barreau set. Okay. Every closed subset of R is a Barreau set. Why? Because closed set, by definition, are depending on which definition you choose. Okay, but basically, closed set can be defined as complements of open set. And as we all know, sigma algebra is closed under complement. So closed sets are Barreau set. Okay, every countable set is a Barreau set. Why? Because a countable set can be written as a countable union of singletons. And each singleton, a singleton is a closed set. So you have B, okay, a countable set is a union of countable closed sets. Therefore, it is closed. Okay, so that's a nice result to know. Every half open interval is a Barreau set. This way, because you can use an approximation argument. Okay, so this is A, this is B. Of course, here we're using the interval with a square bracket on the left and round bracket on the right as an example. You can easily apply the same argument to say interval is open at A but closed at B. This is also a Barreau set. So how do we do that? Well, you can use a approximation argument. So A minus 1 over K, so is a little bit less than A, see? A minus 1 over K. And then as K increases, the left endpoint moves towards A. And so by taking all the intersection, the left endpoint approaches A. So that after taking intersection, only A is left, and every the left endpoint, only have A. Okay? Everything less than A is squeezed out by the infinite intersection. And as we shown earlier, countable intersection is also closed in sigma algebra. Right. So the thing is, the argument is every open interval A minus 1 over K and B is a Barreau set. Their countable intersection is also a Barreau set. And this intersection is A to B. Right? Left open, right, left closed, right open. Okay. So let's just, for the sake of practicing, let's write the second interval as an infinite intersection. It's really easy to do. So you can write it as the intersection over k a open b plus 1 over k open. Same idea. Okay? Every half open interval is also a Borel set. Okay, and lastly, f from R to R is a function. By the way, these results needs to be memorized, I think. Right? Of course, memorization is based on understanding. The reason we memorize result in math is not because these are passive information to be absorbed, but rather these are shortcuts. These are shortcuts. Of course, in principle, you should be able to construct the theory from scratch. But the more results you have in your arsenal, the more proficient you are with constructing arguments, right? But if you only memorize the result without understanding them, then you can't really use them, right? Because you cannot spot situations where these results are useful. Okay, so that's why when we solve exercises and examples, we don't just treat them as chores. Okay, you do them and you solve them and you move on as if they never existed. We take everything we proved ourselves or in the book as potential ammunition for future combat. Okay, so that's the idea here. Math is very cumulative. We don't need to say that at this level. Okay. If f from R to R is a function, then the set of points at which f is continuous is the intersection of a sequence of open sets. And thus is a Borel set. So this is, hang on, the set of points at which f is continuous is the intersection of a sequence of open sets. The exercise 12 of this section. So this is interesting. I think I'm not super familiar with this result, if at all. Okay, let's go to 12. From f from R to R is a function. So this is a nice exercise. We should do that. Okay, nice. So let's summarize what we have here. Hold on a second. Well, let's come to the examples Borel set. So the last one seems particularly interesting. The definition. Let's give it a notation, shall we? Borel sigma algebra. Borel sigma algebra, we usually write BR. Is the interval A to A is equivalent? Yes. A to A is a valid expression. Yes. A to A, that is a valid expression, because when you write A to B, this just means x in real such that x is greater than equal to A, less than equal to B. Apply this definition, then A to A is just x in real, x greater or equal to A, less than or equal to A. Of course, this is equivalent to just singleton A. So this is valid. Borel sigma algebra is the sigma algebra generated by open sets of real. So that's the definition. Okay, and let's look at some examples. So I just want to, perhaps getting a little bit ahead of ourselves, checking a collection of subset is a sigma algebra. It's not always easy. Okay, we have the definition of sigma algebra, but checking, if you can already see here, I mean, even for this finite situation, we need to do some work, right? For this finite collection, we need to do some work. In general, proving a collection of subsets is a sigma algebra is not easy. So you need more machineries, okay, which we will introduce later. It's like the monotone class theorem. So it's to establish a collection is a sigma algebra. All right. So let's continue with these examples. Examples. One, closed set. Examples of Barreau set. Yeah. What does Barreau sigma algebra have to do with Barreau sets? So Barreau sigma algebra is a collection of subsets. Right. The elements in Barreau sigma algebra are called Barreau sets. Barreau sigma algebra is a collection of subsets of real, and the elements in it are called Barreau sets or Barreau subsets. So one is closed set, two is countable sets, three is half open intervals, and four is perhaps more interesting. Four, let's try to summarize in a second. In one sentence. So the set of points at which f is continuous, the points of continuity is a Barreau set. Of f from R to R. And that's exercise 12. Okay. So yeah. If f closed, usually f is used to denote closed set. Then R minus f is open. Okay, countable sets. If B is countable, then B is a countable union of closed set. Half open interval A to B, I write it as infinite intersection. The other direction, let's say A to B, left open, right closed. A, B plus 1 over K. K greater or equal to 1. Okay. So let's do exercise 12, shall we? Here. It seems like an interesting problem. Okay. Let's just put this down in our notes. Okay. So see how the argument is constructed. So here it says for k in z plus, right? So for k in a positive integer, then gk defined as the following. Okay, is defined as following. is an open subset of real for each k. GK is defined as follows. Is this collection of points A in real such that there exists delta such that FB minus FC absolute value is less than 1 over k for all BC in A minus delta A plus delta. Okay, prove that GK is an open subset. Okay, so let's remind ourselves the definition of open set, which I'll put it on the side. I just wrote that definition. E as a subset of R is open if every point in E is an interior point. If for all x in E there exists epsilon greater than 0 such that x minus epsilon x plus epsilon is contained in E. This is the definition of open set. So let's use that definition to prove GK is an open subset. Proof. A. So let's first let K be in Z plus. Let K be in Z plus. We want to show that GK is an open subset. So for that, let's let A in GK. Right? Let A in GK. Need to show there exists epsilon greater than 0 such that A minus epsilon, A plus epsilon is contained in GK. Okay. All right. So how do we go about finding this epsilon? So typically for this sort of existence proof, typically speaking, some sort of backward reasoning is needed. Right? So you want to construct or scratch work is needed. So you want to construct the epsilon and then show it works. The choice of epsilon is often found on scratch work and is not shown in the actual final proof. So therefore, this kind of proofs may look a little bit weird or unnatural for beginners because you're not given in the final proof how epsilon is found. Okay, it's simply a verification. All right, so how do we find this epsilon? We need to understand the definition. We need to understand this definition. So for k here is now fixed. Okay, just consider k be equal 1, for example. We know that A is in GK. Okay, since A is in GK, let's use that. Since A is in GK, okay, there exists delta greater than 0. So this delta now is treated as a constant. There exists delta such that FB minus FC absolute value less than half K for all BC in A minus delta, A plus delta. A plus delta. So now what do we want? We want to show this inclusion relation. We want to show this inclusion relation, so we need to suppose X is in A minus epsilon, A plus epsilon. We need to show X is in GK. We need to show X is in GK. So here we have this little delta here. we need to construct this. By the way, this little delta works for A. Works for A. So for every little A, there exists delta blah blah blah, satisfy the property. So we want to show that X is in GK also. So that means we, as we mentioned, we need to construct a delta that is particular to X. Does the same delta work here? So that's the obvious candidate, right? So does the same delta work here? Well, not necessarily. So here let's draw a little picture, okay? So imagine this is A minus delta, A plus delta. Open interval, okay? Everything in this open interval, if you pick a pair of points BC in this open interval, B here, C here, then the function, which I draw as a continuous function, but it doesn't have to be, okay? The function f is general, it doesn't have to be continuous. But basically fb minus fc absolute value is less than 1 over k. So this difference is less than 1 over k. So we want to show there exists a delta such that a minus epsilon, a plus epsilon is in gk. So can we just use this delta as the epsilon? Can we just use this delta as the epsilon? If we can, then we're done, right? So let's try to prove that. Okay, let's try to prove that. So let me let's write a little claim. If it works, then it works. If it doesn't work, then let's think about something else. Let's claim that for this particular delta, a minus delta, a plus delta is in gk. So to see this, suppose x is in a minus delta, a plus delta, and see what's going on. Okay, so x is in here. Well, you can construct an interval because this is open. This is an open, so you can construct an interval centered at x, and it's still containing a minus delta, a plus delta. That is contained in it. So this is the idea. I'm drawing this is x plus epsilon, x minus epsilon. Okay, so then there exists epsilon greater than 0 such that x minus epsilon, x plus epsilon is contained in a minus delta, a plus delta. This is because a minus delta, a plus delta is open. So we write, suppose, to see this, suppose x is in x minus a minus delta, a plus delta, and open set. And then you have this. And then you have this. So now everything in here, for all, let BC in x minus epsilon x plus epsilon. Okay, so therefore B, C are both in A minus delta, A plus delta, and it satisfies this inequality. And as a result, FB minus FC absolute value is less than 1 over K. So what does this say? It says for every BC in x minus epsilon x plus epsilon, FB minus FC absolute value is less than 1 over K, and as a result, x is in GK. X is in GK. So you start from an arbitrary x in A minus delta A plus delta. You show that x is in GK, so therefore this proves the claim. This proves the claim. So that's the illustration here. So we can simplify the paragraphs a little bit. Okay, so let's just erase that. Erase that. So that's it. The picture on the side. This is the claim, and we're done. So the conclusion is for every arbitrary k, if A is in GK, then there exists a delta greater than 0 such that A minus delta A plus delta is in GK, is contained in GK. So therefore GK is open. The claim means GK is open. And we're done. I want to prove that GK is open set, so we're done. All right. B, prove that the set of points at which f is continuous equals this. Equals the intersection of GK. Okay. B. Okay. Well, how do we go about showing that? Let's denote CF continuous, right, as the set of x A. Let's use A. Real such that, you see, this is perhaps a good strategy we should keep in mind. So basically, we want to, whenever possible in measure theory, write a set as a countable intersection, countable union, that sort of thing. This seems to be a rather general strategy. You see, like you see, 3 half open intervals. We did that. We wrote that as a countable intersection. So even though exercise 12 is considerably more complicated, the idea is still write a set as a countable intersection of open sets. Okay, so CF is the set of continuity. A in R such that F is continuous at x equals A. F of x is continuous at x equals A. So that's the idea. So that's the set we need to show. CF is the intersection of GK, k greater or equal to 1. So this is what we want. Of course, this amounts to a double containment argument. So let's first show the one direction. Okay, so let x is let A to be in CF. So this way, F is continuous at x equals A. Okay, so this, by the way, the definition of GK looks very similar to the definition of continuity. So why don't we just review that as well? Do a little quick review of the epsilon delta definition of continuity. Okay, so here, it's what we need from elementary analysis. Okay, we don't cover elementary analysis from ground up, but we cover what's needed on a need-to-know basis. Okay, so let f from R to R be a function. F of x is continuous at x equals a if for every epsilon greater than 0 there exists a delta. Oh no, there exists a for every epsilon greater than 0 there exists a delta greater than 0 such that x minus a absolute value less than delta implies f of x minus f of a absolute value is less than epsilon. Classic epsilon delta definition of continuity. All right, so let's continue. Here, let a be a point at which f is continuous. So we want to show that we need to show it's in the intersection. So that is to say, we need to show it's in the intersection. Need to show a is in GK for some k in z plus. That's what we need to show. And then it's just a matter of applying the definition of continuity. Since f is continuous, f of x is continuous at x equals a, it follows that there exists epsilon greater than 0. Actually, no. We need for every epsilon. We have for every epsilon. Hang on. Oh, actually, here I wrote need to show wrong, not for some. Intersection must for all. For all. Hang on, my bad. For all. For all. For all k in z plus. Okay, so that changes things a little bit. So we start from let k in z plus. Next sentence should be for let k in z plus. For let k in z plus, okay, since f of x is continuous at x equals a, let's try to apply the definition of continuity. Okay, so basically we're picking the epsilon to be 1 over k. This is an obvious choice. So there exists delta positive such that f of x minus f of a, actually, you know what, let's use bc. For f of b minus f of c, absolute value less than 1 over k whenever bc is in a minus delta, a plus delta. Because of continuity, 1 over k can be arbitrary, because epsilon is arbitrary. So this works for all k. This works for all k, and as a result, i.e., a is in gk as needed. And so this proves the one direction. CF is contained in the intersection of gk, so we're done. As for the opposite direction, it shouldn't be too difficult. So let A to be in the intersection of gk, k greater or equal to 1. Right? You need to show f is continuous at a. F of x is continuous at x equals a. Okay, so use the epsilon delta definition. Start with let epsilon greater than 0. Let epsilon greater than 0. Okay, since a belongs to every single gk, okay, since a belongs to gk for all k greater than 0, okay, we can pick k. We can pick k in z plus such that 1 over k is less than epsilon. This is possible due to the Archimedean property. Okay. Such that 1 over k is less than epsilon. Okay. Then there exists delta such that f of b minus f of c absolute value is less than 1 over k and thereby less than epsilon whenever b and c are in a minus delta, a plus delta. So this proves continuity. Okay, proves continuity. You need for every arbitrary epsilon there exists delta such that whenever x, whenever actually you need b. It exists. Hang on a second. Actually, let's write one more sentence. Okay, so this is whenever. So okay, so this way, therefore, for this particular delta, fx minus fa absolute value is less than epsilon whenever x is in, because a is always in a minus delta, a plus delta. Just need x is in a minus delta, a plus delta. That is the same as saying x minus a absolute value is less than delta. Therefore, f is continuous at x equals a as needed. Okay, so two sides together gives you the equal. The two sets are equal. Okay, and see, conclude that the set of points at which f is continuous is a Borel set. So that's easy because gk for each k is open. Therefore, gk belongs to the Borel set. Is it possible to understand these by self-studying without a teacher as a non-math graduate? So of course, non-math is a huge set. Non-math graduate is a huge set. It has less to do with formal credentials, but rather a familiarity with proof writing. Okay, and some elementary analysis preparation. So what I just did here, what I just did here are all just repetitive applications of fundamental skills in proof writing. So I think that's the biggest obstacle for any non-math graduate to approach a subject like measure theory. Because for the most part, what you're doing is masterful application, if I do say so myself, of fundamentals. So what I'm performing here, okay, are for this particular question, for example, so you just need a general strategy of how to prove mixed quantifier statement for all there exists and so on. So for that you need a preparation, not just, you don't need a math degree, okay, you just don't need a although math degree usually covers that, just basic proofwriting skills. Okay. And for that, if you guys want a good reference, let me just provide a good book. I mean, it's just my experience, okay? I don't like recommending books that I personally never read. But here's a good one. It's called The Tools of Mathematical Reasoning by Tamara J. Lakins. So it's not a very long book, and I think it's quite approachable without instructor. So there's that. So just for proofwriting skills. And with that, okay, the thing is, with proofwriting skills, the entire mathematics opens up to you. And it doesn't matter what your formal credential is. If you have proofwriting skills, then entire math opens up to you. Right. I don't think that's an overstatement. Okay. Of course, it takes time. Okay. If you don't have good skills in writing proofs, then the Axler is perhaps a little bit too difficult. Because if you don't have proofwriting skill, you cannot even tell something is proved versus something is claimed. You know, something is proof or is just heuristics. Okay, so that's the most important prerequisite. Okay, let's coming back to the final part. I mean, this is already done. GK is open. So since GK is open, for all K, GK belongs to the Borel sigma algebra. Belongs to this Borel sigma algebra of all K, then the intersection K greater or equal to 0, then that's an element in BR. So this is a nice example, just a little bit less trivial. Even though the proof is actually quite straightforward. You just need a definition of continuity. Okay. The set of continuity is a Borel set. Okay, cool. Borel sigma algebra, of course, being the most important sigma algebra of all time, probably. Okay. And now we need to move on to a new notion, I believe, called measurable functions. So we're making a lot of progress today, which is quite nice. Okay, so here, let's continue with the last block of discussion on Borel set. The intersection of every sequence of open set is a Borel set. By sequence, of course, we mean a countable collection. Over time, I decided I don't like the idea of automated theorem proving. Doing mathematics requires personally trying to prove things. Yeah, automated theorem proving is a math field on its own, right? I mean, the idea is not to dismiss technology, but simply the idea is, okay, so certain proof writing can be automated, right? That's, of course, that's a valid goal. It's just because let's say you need to prove a theorem by checking 10,000 cases. And that's an excellent job for the machine, but you still need a proof for that to work, right? You need a proof for saying things like, oh, if you just check these 10,000 cases, then you're done. Then you can give your task to the machine, right? So automated theorem proving can absolutely be a helper, and it's still, as far as I know, a relatively new field, and it's still under development. And there are important theorems that are being proved by automated theorem proving. But that on its own is not a replacement for learning to prove things. Okay. Right. substitute of thinking simply does not exist. Okay, that's simple. End of the story. The intersection of every sequence of open subset of R is a Brillouin set. However, the set of all such intersections, this is the difference here. Every sequence of open subset, that's a countable collection. But all such intersection is not necessarily a countable collection. It says it is not obvious, but it is not closed under countable union. Hang on a second. However, the set of all such intersections is not the set of Brillouin set. Wait. However, the set of all such intersections. Hang on a second. I am not sure what's going on. The intersection of every sequence of open sets of R is a Brillouin set. That's obvious. However, the set of all such intersections is not the set of Brillouin set. So what it is saying is that, let me just put that down. Fact. Denote S as the set E as a subset of real, such that E is an intersection. E is the intersection of some sequence of open set. E equals the intersection of GK, G greater or equal to 1. Yeah, that's Vermont, you're right. Yeah, I'm trying to give that, write that down. So E equals the intersection of GK for some sequence GK of open set. So denote S to be this. S is the collection of subsets that can be written as the countable intersection of open sets. And the fact is, S is not the same as the Brillouin sigma algebra. It says this is not obvious, but it is not closed under countable union. That's the reason. If you're going to prove it, you can say suffices to show S is not closed under countable union. Now, the set of all countable, let's read that. The set of all countable unions of countable intersection. The set of all countable unions of countable, hold on a second. The set of all countable unions of countable intersection of open subsets of R is also not the set of real set. This is a general property of set theory, not specific to Borel and sigma algebra. Okay. Again, this is not obvious, but it's not closed under countable intersection. And so on ad infinitum. There is no finite procedure involving countable unions, countable intersection, and complement for constructing the collection of Borel set. There's no finite procedure involving countable unions, countable intersections, and I am very confused here. For constructing collection of Borel set, we will later see that there exist subsets of R that are not Borel set. However, any set of R that you can write down in a concrete fashion is a Borel set. Okay. Here. Next it says the set of all intersections. Let's write it this way. The set of all intersections S is the set of all intersection of GK such that GK is G1 all the way blah 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 are open. Open set. So this is not the Borel sigma algebra of on R. This is not the Borel sigma algebra on R. Suffice it to show S is not closed under countable union. How do we do that? Well, you need to construct a sequence in S whose countable union is not in S. Right? S is a collection of all. S is a collection of intersections of open sets. Well, it is well known that the intersection of open sets aren't necessarily open. Tricky, right? Where do we even get a clue of how to construct such a sequence in S? This is fact number one. The Borel sigma algebra is not the set of intersections of open sets. Fact number one. Because I have no idea how to construct the sequence right now. Fact number two is what? Factor number two is the set of all countable unions of countable intersection. The set of all countable union of countable intersection is also known. Okay, this is fact two. Call it T. T is defined as
the countable union of countable intersection. So that's the countable union. Countable intersection of open set, that's just S. So let's say L greater or equal to 1 union of EL, where E1, E2, and so on is in S, scripted S, above. And T is not real sigma algebra of R either. How do we show that? Thanks for the recommendation. The T is not a real sigma algebra either. And then it says ad infinitum. There's no finite procedure involving countable union, countable intersection, and complement for constructing the collection of Barreau set. Once again, it's highly non-trivial. Huh? The proof says T is not closed under countable intersection. Suffices to show can we AI it? Okay. Guys, I'm going to AI and see if we can get some sort of idea of why this is true. Okay, so suppose, let's consider show that the set of countable intersection of open sets in R is not closed under countable union. Oh, a standard counting example is built from rational. Hold on a second. So that's let Q be Q1, Q2, and so on be an enumeration of the rationals. For each Qn, the singleton Qn is a countable intersection. Indeed, yeah, it's just a singleton. You can always write it that way. Each open interval is open. Now consider the countable union. I remember sisters just pull that out. Yes, very possible. I mean, the advantage of AI is it has a huge knowledge base. Right, so here we have, so every singleton is a G delta set. Oh, let's try not to use this terminology because it assumes more background. But our one proof uses bare category. Okay, yeah, okay, it uses the bare category. Okay, perhaps it's a little bit deep for what we're doing here, but let's just try to use as elementary tools as possible. Okay, this is, we want to show that what we want to show the countable intersection. The set is not closed under countable union. How do we construct countable union? Q is not a G delta subset of real. R is so G is not so Q. Okay, so Q is so Q is not a. Hold on a second. What do we want here? What we want it is not closed under countable union. It's not closed under countable. So basically, we want to show that Q is not an intersection of open set. Right? Q is not an intersection of open set. So how do we show Q is not a countable intersection? Some sort of contradiction, perhaps? The standard proof uses bare category. Is there a more elementary argument? A slightly more elementary. Okay. If you rather avoid the language of Komiger, there's a nice argument using intervals. Okay. Suppose Q is the countable intersection of UN. And that's cool. Right. So since every UN is open and contains all the rationals, each UN is dense. So what's the conclusion here? Is it a constructive version of bare category as presented an equivalent formulation of Bare's theorem? Okay, so some sort of bare category argument needs to be used. So, but this is not super important for our purpose. Okay, this is not super important for our purpose. I guess the idea is we have this claim. There's no finite procedure involving countable union, countable intersection, blah, blah, that can construct the collection of Barreau set. So remember, the notion of Barreau set, or actually the notion of smallest sigma algebra in general, is not a constructive process. It's like you cannot list its elements, right? And in fact, if you can list its element, that will be countable. A sigma algebra can only be, it is a result, actually, I'm getting ahead of myself. It is a result that a sigma algebra can either be finite or uncountable. But it turns out that for Barreau sigma algebra, you cannot even give a descriptive, a constructive procedure, so to say, in the sense that there is no finite procedure including countable union, countable intersection, and so on, to construct the collection of Barreau sets. The notion of Barreau sets is defined in a non-constructive manner. Like in the proof here, proof of 2.27, you're taking the intersection of all sigma algebras containing open sets on real. Right, so yeah, that's, I guess, the best thing we can say at this point. Right, so that's the main takeaway here, even though there's details we haven't managed to prove. Let me just put a little bit of notes here. Okay, proof requires a bare category. Perhaps we should do a separate stream on more elementary analysis. Bare category theorem is a result in metric spaces. I think it can be constructed when you go through countable ordinals. I asked Leo earlier, something like UNSN. Yeah, actually, guys, my background in set theory or axiomatic set theory if it ever if actually requires that, is pretty weak. Okay, so for these fundamental topics, go ahead and ask Leo. Okay, I'm mostly a more applied mathematician, if I can call that myself. Okay, so I'm not quite sure, like, how do you like he mentions there's something like some sort of transfinite induction. I have no clue how that works, so perhaps it's not even relevant here. But basically, it's fair to say that to prove this fact requires arguments that are equivalent to bare category theorem, okay, which is a little bit far from our main goal. So that's why I'm skipping the proof. Okay. The moral is let's put it down here. There's no finite procedure. Okay, let's copy that down from Maxwell. That's the moral here. And I think we can live with that for now. There's little harm in not being able to prove this fully. Okay, so let's continue to the next topic on measurable theory. Measurable theory, measurable functions. If you're doing measure theory like this, you're definitely overlapping with pure math. Yeah, I know, exactly. I mean, the whole notion of pure versus applied math is completely arbitrary. Okay, I don't believe there's such a thing called pure versus applied mathematics anyway. It's just my training. Okay, it's just my training. It's not. I'm not saying, oh, those are beyond my. I don't need to care about them ever. So it's just because of my background does not involve a very extensive training in more fundamentals of set theory. So yeah, I pretty much only encounter them on a need-to-know basis. It's not a systematic exposure. Okay, so this is just an unfortunate byproduct of my background. It's not like saying I don't need them. Okay, it's an unfortunate reality that due to my limited training, I'm not familiar with them. Okay, perhaps there's an overarching theme of the channel. Okay, the philosophical underpinning of the channel is that there's no such thing as pure versus applied mathematics. This is just division of labor at best. There's no scientific difference between them. Okay, so I'm always open and eager actually to learn more about what is quote-unquote traditionally called pure mathematics. This is just a purely sociological distinction, not a mathematical one. Anyway, so here we have some basic set theory. Actually, I made a bunch of quizzes based on these. Inverse images, and whatnot. There's a lot of things that can confuse even veterans. So okay, cool. Or the concept of ordinals, yeah. Once again, ordinals should be still. I mean, I'm struggling to see why is ordinal relevant here, but still, perhaps it's just due to my limited understanding. Okay, but anyway, let's go. Here, let's take a little bit of a break. Okay, let's do something easy. Inverse image. Okay, the inverse image can be visualized as follows. So you have a set X, that's the domain of F, and you have a function Y that maps from X to Y, and then you have a subset, say A, of Y. Okay, the preimage F inverse of A is simply the collection of X such that F of X is in A. So that's the inverse image. Okay, and here there are some simple examples. Consider the function F of X equals sine of X from 0 to 4 pi. Let's draw a diagram. This is first year stuff. 0 to 4 pi. So the inverse image of 0 to infinity This consists of the value of x such that f of x is positive. So it's 0 to pi, this part here, union with 2 pi to 3 pi. Okay, straight from the diagram. The inverse image of 0 to 1, closed interval. Okay, so because when f of x is positive, it is less than or equal to 1. So it contains the value of x that is between 0 to 2 pi, 0 to pi, closed interval in this case because of the closed interval sign here. Okay, and closed interval here. And lastly, you have 4 pi. Okay, and f inverse of minus 1, just a singleton, contains 3 pi over 2 and 7 pi over 2. And lastly, the inverse image of 2 to 3. That's impossible because sign cannot be greater than 2. So that's just the empty set, as you should verify. So this is, I will not write down the detailed argument because this is quite obvious and it's not difficult to verify. If you do wish to formally verify this, you use a double containment argument because it's a set equality. These are all set equalities, so you use a double containment argument. I will not do so for the sake of this stream because that's basic proof writing stuff. But one thing to pay attention, though, is perhaps worth reminding ourselves is that notice the nature of all these results. Notice the nature of all these results. We observe that the preimage of all, or inverse image, the inverse image or the preimages of all the open sets are open. And the preimage or the inverse images of all the closed sets are closed. And this is not a coincidence at all. This is because f of x is a continuous function. So continuous functions have this property. The preimages of open sets remains open and the preimages of closed sets remain closed. In fact, that's the definition of continuity in topological spaces. If the preimage of an open set is open for all open sets, then f is open. So not what is f is f is continuous. Okay, so that's why we wish to pay attention to this result here. Okay. Next up we have algebras of inverse images. This is once again very attractive properties of inverse images. Inverse images has good algebraic properties as shown in the next two results. So basically the idea is common set operations, complement, union, intersection, and actually arbitrary union, arbitrary intersection commute with f inverse. They commute with f inverse, so this is super nice. In general, this sort of commutativity does not work for images, but works for inverse images. Okay, so for the let's say let's prove one. Okay, so Axler proved A and B, and said C is proved in the same fashion as B, with union replaced by intersection, for some replaced by for every. You know what? Let's do that, and just take these results as granted. Okay, so first let's put down the result in our notes, and then we'll prove C, because this should be quite straightforward. Once again, the proof of ABC should be covered in a first-year course on proof writing, which I provided the link, not the link, but the name of the book. Okay, Tools of Mathematical Reasoning. So this sort of exercise is very standard for introductory proof writing courses. Okay. All right, so here, definition: f from x to y, f inverse of A is defined as x in big X such that f of x is in big A for A subset of y. Okay, so that's the definition. Properties. property. So you have these nice properties of the inverse image. 1. F inverse of y minus a complement basically is x minus f inverse of a. The complement of inverse image, the complement of the inverse image is the inverse image of the complement. We love that. B. F inverse of the union, okay, is the union of F inverse of A. Okay, so C. F inverse of the intersection is the intersection of the inverse images. So here union stands for the union of over some index set, and the intersection is the intersection over some index set as well. It does not have to be countable. Okay, so that's the proposition. Let's prove C, and this should be quite easy. So usually what you do is you write a double containment argument, but here you can actually convert every sentence into, so you can use if and only if all the way, but I don't recommend that because you know, if you're absolutely sure, you can do this sort of double implication, then go ahead and do it. But typically when we write the proof of set inequality, we prove both ways. This is way it's easier to follow, and you're less likely to get confused because sometimes double implications can be tricky to verify. So here, actually, guys, I might need to leave in 10 minutes. Because my mom wants to call me. Okay, family is important. So let me just finish part C, and then we'll close up the stream tonight. Okay, so that's a solid 4 hours tonight. Okay, so here let x be in the inverse image of the intersection of A. Then f of x is in the intersection of A. So this means f of x is in A for every A. Okay. All right. So this means x is in inverse of A for all A. And therefore x is in the intersection of A. Okay. Opposite, let x be in the intersection of f inverse A, then x is in the f inverse of A for every A. So f of x is in A for every A, then the f of x is in the intersection of A. Okay. Then x is in the inverse image of A, inverse image of the intersection of A. So we're done. All right, guys. So yeah, sorry for ending the stream a little bit earlier, but because my mom wants to call me. Okay. Thank you very much for watching the stream, and I'll continue next week. So we made good progress today. Okay. Next week, we should talk about what's the next section. Next week, I finally talk about measures. That'll be awesome. Okay, we can finally introduce measures. Okay. Okay. And the main goal of this chapter, chapter 2, is to construct the Lebesgue measure. To construct the Lebesgue measure. So remember, we defined outer measure. And now we're doing sigma algebra, especially Barreal sigma algebra. And it turns out that if we restrict out the measure on the Barreal sigma algebra, you do get a measure. So that's one of the biggest result of this chapter. So this way, if you manage to construct a big measure on real, probabilistically speaking, we have defined uniform distribution. Uniform distribution is equivalent to the big measure. All right, and of course, with the uniform distribution at our disposal, you can transform it to get more complicated distribution, like the exponential distribution and whatnot. Okay, but we will follow the order of the textbook. Okay, we're well on our way to constructing the big measure. All right, guys, I'll see you guys next week. Bye now.